You trust that time is steady. A second is a second. An hour is an hour. Time, you assume, is the one thing in the universe that is the same for everyone. That trust is wrong. The clock at the top of a tall building ticks faster than the clock in its basement by amounts so small that only atomic clocks can measure them. The effect is real. Hundreds of experiments have confirmed it. Einstein worked this out in 1915, and every test we have run since has confirmed him. Time is not a constant. Time bends and stretches. It depends on where you are and what is happening around you. And then there are black holes. What I want to walk you through is what time actually does at the edge of a black hole, not the cartoon version, not the science fiction version, the real version that comes out of Einstein's equations and is now being measured directly by observatories around the world. Because here is the thing most people get wrong about black holes. They think the terrifying part is what is at the center. They think the danger is the singularity, the crushing density, the place where matter ends. The terrifying part is not the center. The terrifying part is the edge. The edge has a name. The event horizon. It is the boundary around a black hole beyond which nothing, not even light, can escape. And the moment you cross it, time itself stops behaving the way it has behaved for every other moment of your life. That is the recurring thread of this story. The event horizon. We will return to it again and again, and by the end of this video, you will understand it differently than you do right now. If the strange edges of physics keep you company at night, you are in the right place. Subscribe and settle in. The strangest part is not the math. It is what happens at one specific distance from the center, a distance you can calculate from a single number, the mass of the black hole. The equation that defines that distance was solved by a man named Karl Schwarzschild in 1916, while he was serving on the Russian front in the First World War. He sent his solution to Einstein in a letter, and within months he was dead. The equation he left behind broke time. We will get to exactly how. To understand why this matters, you have to understand what time was supposed to be. For most of human history, time was the most obvious thing in the world. The sun rose, the sun set, the seasons turned, the moon waxed and waned. Whatever time was, it was the same for the farmer in the field and the priest in the temple and the sailor on the ship. A second was a second. A day was a day. A year was a year. The universe might be vast and mysterious in many ways, but the steady, forward march of time was not one of them. The first great formalization of this intuition came in the year 1687, when an English mathematician named Isaac Newton published the Philosophia Naturalis Principia Mathematica. The Principia is, among other things, the founding document of classical physics. In it, Newton laid out his three laws of motion, his law of universal gravitation, and his definition of time itself. Absolute, true and mathematical time, he wrote, of itself and from its own nature, flows equably without relation to anything external. It was a beautiful sentence. It was also wrong. Newton's universe was a clockwork, a vast, intricate, eternal mechanism with God as the original watchmaker. Time flowed through it like a great river, the same river for every observer, the same current for every clock. A second on Earth equaled a second on the Moon. A second on Mars equaled a second in the deepest interstellar void. The cosmos might be filled with matter moving and orbiting and colliding at every scale, but the underlying time against which all that motion took place was absolute, universal, immutable. This intuition held for more than 2 centuries, generations of physicists built on Newton's foundation. The Industrial Revolution ran on Newtonian timing. The first railways scheduled their trains by it. The first transatlantic telegraph cables synchronized continents by it. By the late 1800s, the consensus that time was a constant, universal property of the cosmos had become so deeply embedded in the way humans understood reality that almost nobody thought to question it. There was a single, persistent, loose thread: light. In the 1860s, the Scottish physicist James Clerk Maxwell had derived a set of equations describing the behavior of light as an electromagnetic wave. Maxwell's equations were extraordinarily successful. They predicted radio waves before radio waves were detected. They explained why light travels at exactly the speed it does. They unified electricity and magnetism into a single phenomenon. But Maxwell's equations had a strange property. They gave the same speed of light for every observer, regardless of how fast that observer was moving. Light, according to the math, always traveled at 186,000 miles per second. Whether you were standing still or running at half the speed of light, you would measure the same number. This was not what Newton's universe predicted. In a Newtonian cosmos, if you were running toward an oncoming light beam, you should measure the light moving faster relative to you. If you were running away, slower. For decades, physicists tried to explain this away. They proposed a luminiferous ether, an invisible medium filling all of space, through which light propagated and against which Maxwell's constant velocity was measured. In 1887, two American physicists named Albert Michelson and Edward Morley conducted one of the most famous experiments in scientific history, attempting to detect Earth's motion through this ether by measuring the speed of light in different directions. They found nothing. The ether did not exist. The speed of light really was constant for every observer. Something had to give. And in 1905, working at a patent office in Bern, Switzerland, a 26-year-old physicist named Albert Einstein published the paper that revealed what? If the speed of light is constant for every observer, Einstein argued, then time itself cannot be constant. The two ideas are mathematically incompatible. If you hold one, you must release the other. And the experimental evidence had already chosen which one to release. Time, Einstein wrote, depends on the observer. A moving clock ticks slower than a stationary one. The slowing is small at everyday speeds, but it becomes substantial as you approach the speed of light. At ordinary velocities, it is too small to notice. At cosmic velocities, it transforms the universe. This was the theory of special relativity. It was published in a paper titled On the Electrodynamics of Moving Bodies, and at first, almost nobody read it. The first experimental confirmation that special relativity was right took decades to arrive. The technology to measure time precisely enough simply did not exist in 1905. Mechanical clocks could not detect changes of microseconds. Pendulum clocks were too slow. Even the most accurate quartz clocks of the early 20th century could not reliably measure relativistic time dilation at the velocities humans could actually generate. The breakthrough came with the invention of the atomic clock in the 1940s and 50s. An atomic clock measures time by counting the oscillations of atoms, typically cesium or rubidium, vibrating at incredibly stable frequencies. The cesium atom oscillates at exactly 9,192,631,770 times per second. This frequency is so stable that the modern definition of the second is based on it. 1 second is, by international agreement, 9,192,631,770 oscillations of a cesium-133 atom. With atomic clocks, physicists could finally test Einstein's prediction. In October of 1971, two American physicists named Joseph Herfield and Richard Keating loaded 4 cesium atomic clocks onto commercial airliners. They flew the clocks around the world, first eastward, then westward. They compared the readings to identical atomic clocks that had stayed stationary at the United States Naval Observatory in Washington, D.C. The flying clocks were out of sync with the stationary ones, by exactly the amount Einstein had predicted. The eastward clocks had lost approximately 59 nanoseconds. The westward clocks had gained approximately 273 nanoseconds. The difference was due to the combined effects of velocity, which slowed the clocks slightly, and altitude, which sped them up slightly more. It was a small experiment. It used commercial airline tickets. It took 4 cesium clocks the size of suitcases, and it confirmed, beyond any reasonable doubt, that time is not what Newton said it was. Haefel-Keating was the first widely publicized confirmation of relativistic time dilation, but it was not the first laboratory verification. That had come 12 years earlier, in a Harvard physics tower. In 1959, 2 American physicists named Robert Pound and Glenn Rebka conducted what would become one of the most elegant experiments in 20th century physics. They worked in the Jefferson Physical Laboratory at Harvard University, in a tower roughly 22.5 meters tall. They positioned a source of gamma radiation at the bottom of the tower and a detector at the top. The gamma rays in question were produced by iron 57 atoms, which emit a specific frequency of radiation when their nuclei transition between energy states. According to general relativity, the gamma rays traveling upward against Earth's gravity should lose a tiny amount of energy on the way up. This energy loss should manifest as a redshift, a slight decrease in the frequency of the radiation arriving at the detector relative to the frequency emitted at the source. The predicted effect over 22.5 meters of altitude was approximately 2.5 parts in 10 to the 15th power, a staggeringly small number. The gamma rays would arrive at the detector approximately 2.5 quadrillionths slower in frequency than they had been emitted. Pound and Rebka measured this. The experiment used a technique called the Mössbauer effect, which allowed them to detect frequency shifts so small that previous instruments could not even acknowledge the question. They confirmed Einstein's prediction to within 10% in their first paper. They refined the result to within 1% 2 years later. A clock at the top of a 22-meter tower really does run faster than a clock at the bottom by exactly the amount general relativity predicts. The experiment cost almost nothing by modern standards. It used a single building, a single radiation source, and a few graduate students. It was the first direct laboratory verification of gravitational time dilation, and it has been repeated, refined, and extended dozens of times since. By the early 2010s, the precision had grown to the point where physicists could measure time dilation produced by gravitational differences of just a few centimeters. In 2010, the National Institute of Standards and Technology in Boulder, Colorado, used an optical atomic clock so accurate that they could measure the time dilation produced by raising one of 2 identical clocks just 33 centimeters off the ground. 33 centimeters, roughly the height of a stack of textbooks. The higher clock ticked measurably faster than the lower one. This is the smallest verified test of gravitational time dilation ever performed. The clocks used in this experiment are called optical lattice clocks, and they represent a significant advance over the cesium clocks used in earlier experiments. An optical lattice clock uses ultra-cold atoms, typically strontium or ytterbium, trapped in a grid of intersecting laser beams, where they oscillate at optical frequencies hundreds of thousands of times faster than cesium. The result is a clock so precise that, if it had been started at the moment of the Big Bang, it would only now be off from a perfectly synchronized parallel clock by about 1/10 of a second. In 2020, researchers at NIST in collaboration with Giller in Boulder pushed this further. They built a clock so precise that it could detect the time dilation difference between the top and bottom of a single millimeter tall sample of ultra-cold strontium atoms. A millimeter, the thickness of a fingernail. At that scale, the curvature of space-time produced by Earth's gravity is measurable. The atoms at the top of the millimeter sample tick measurably faster than the atoms at the bottom of the same millimeter sample. The clocks are now so good that we can map the gravitational gradient of the universe at scales smaller than a grain of rice. This precision matters because it forces a particular philosophical position on anyone who looks at the data. Time dilation is not a quirk that happens only in extreme conditions. It is not a special case feature of fast-moving particles or strong gravity. It is the universe's default behavior. Every clock at every position is running at a slightly different rate than every other clock. The differences are tiny in your local neighborhood, but they are real, and they have been measured. If raising a clock by 1 foot changes the rate at which it measures time, then the question is not whether time depends on position. The question is how much. The clearest practical answer to that question is sitting in your pocket right now. The global positioning system consists of a constellation of approximately 24 to 31 satellites in medium Earth orbit at an altitude of roughly 20,200 kilometers above the surface. Each satellite carries an atomic clock. The system works by measuring the time it takes for radio signals to travel from the satellites to a receiver on the ground. By knowing the precise position of each satellite and the precise time the signal was sent, the receiver can calculate its own position to within a few meters. For this to work, the satellite clocks must be synchronized to within nanoseconds. Any drift, any disagreement between the satellite clocks and the receiver clocks accumulates into a positioning error. The math is straightforward. A nanosecond of timing error corresponds to roughly 30 centimeters of positioning error. A microsecond corresponds to 300 meters. A millisecond corresponds to 300 kilometers. Now consider what relativity does to those satellite clocks. The satellites are moving at approximately 14,000 kilometers per hour relative to the ground. According to special relativity, this velocity should cause the satellite clocks to tick slightly slower than ground clocks by approximately 7 microseconds per day. Time dilation from motion, Einstein's prediction from 1905. But the satellites are also at high altitude. They are 20,000 kilometers above the surface, in a region where Earth's gravitational field is much weaker than at sea level. According to general relativity, weaker gravity should cause the satellite clocks to tick slightly faster than ground clocks by approximately 45 microseconds per day. Gravitational time dilation, Einstein's prediction from 1915. Combine the two effects, subtract 7 microseconds, add 45 microseconds. The net result is that the atomic clocks aboard every GPS satellite tick 38 microseconds per day, faster than identical clocks on the ground. 38 microseconds. Not a calculation, a measurement, every single day on every single satellite, ticking faster than the watch on your wrist by a precise, predictable, calibrated amount that comes directly out of Einstein's equations. The engineers who built the GPS system in the 1970s knew this would happen. Before launch, they deliberately adjusted the frequency of the onboard atomic clocks so that, once in orbit, they would tick at the same rate as ground clocks. The frequency offset is built into the hardware. If you opened up a GPS satellite and looked at its cesium oscillator, you would find a clock that ticks at 10.229-9999 543 MHz when it should, in a Newtonian universe, tick at 10.23 MHz. The decimal places of correction are the precise mathematical fingerprint of Einstein's two theories combined. Without this correction, the positioning error from accumulated time dilation would be about 10 kilometers per day, every day, compounding. After a week, GPS would put you in the wrong city. After a month, the wrong state. After a year, the wrong continent. The system would be useless. The system is useful. Therefore, Einstein was right. Therefore, time is not constant. There is one more loose thread. If 38 microseconds per day is what very weak gravity does, and Earth's gravity is, on the cosmic scale, extraordinarily weak, then what does the universe do at the other extreme? What does time look like in a place where gravity is not gentle, where gravity is not modest, where gravity is the strongest it can possibly be? where the curvature of space-time is not a slight bending, but a complete collapse. The Schwarzschild radius is the answer, and the man who derived it never lived to see what it meant. In August of 1914, a 41-year-old German astronomer named Karl Schwarzschild was directing the Potsdam Observatory, one of the most prestigious astronomical institutions in Europe. He had been at Potsdam for 5 years. He was widely considered one of the finest mathematical physicists of his generation. His work spanned celestial mechanics, stellar atmospheres, optics, and electrodynamics. He had been elected to the Royal Prussian Academy of Sciences at the age of 40. When the First World War broke out, Schwarzschild volunteered for the German army. He did not have to. He was a senior scientist, a Jewish intellectual, and well over the typical age for combat duty. But he believed it was his patriotic obligation, and he wanted to contribute to the war effort. He was assigned to artillery. By late 1915, he had been deployed to the Russian front, where he spent his days calculating ballistic trajectories for German howitzers, work that drew on the same mathematical tools he had used for orbital mechanics, but applied to shells instead of planets. In November of 1915, while Schwarzschild was at the front, Albert Einstein published the final version of the general theory of relativity. Einstein's field equations describe gravity not as a force, the way Newton had, but as the curvature of space-time itself. Mass bends space. Mass bends time. The motion of objects through the bent geometry is what we perceive as gravity. The equations were beautiful. They were also fearsomely difficult to solve. Einstein himself believed that no exact solution would be found for years, if ever. He suspected the equations would only ever be solvable through laborious approximation. Schwarzschild read the paper in the trenches. Within weeks, possibly within days, he had derived an exact solution. The solution applied to a single, spherically symmetric, non-rotating mass sitting alone in otherwise empty space. It described the curvature of space-time around any such object, from a planet to a star, to whatever the universe might contain that was much more compact than either. The solution was mathematically clean. It was rigorous. It was, by any standard, a stroke of genius. On December 22, 1915, Schwarzschild mailed the solution to Einstein from his post at the Russian front. Einstein replied on December 29th, expressing astonishment. He had not expected anyone to find an exact solution at all, let alone within weeks of his own paper's publication. On January 13th, 1916, Einstein personally presented Schwarzschild's solution to the Prussian Academy of Sciences in Berlin. Schwarzschild never made it home to see it. Sometime during his deployment, he had contracted pemphigus, a rare and brutal autoimmune disease that causes the body's immune system to attack the cells holding the skin together. The blisters that formed across his body were, at the time, untreatable. He was invalided home in March of 1916. He died in Potsdam on May 11, 1916, less than 5 months after Einstein had presented his work to the Academy. He was 42 years old. He left behind a wife, 3 children, and a body of work that ranged across nearly every branch of 19th century mathematical physics. Before the war, Schwarzschild had derived foundational equations describing the transport of radiation through stellar atmospheres, work that astronomers still use today to model how light moves through the outer layers of stars. He had measured the brightness of thousands of stars from observatories in Potsdam, Göttingen, and Munich. He had contributed to the theory of optical aberrations in telescopes. He had written papers on the photographic plate, on celestial mechanics, on the orbits of binary stars. He was one of the most versatile physicists in Europe, and he died with much of his most important work still unfinished. His son, Martin Schwarzschild, would grow up to become one of the most respected astrophysicists of the 20th century, building the field of stellar structure theory at Princeton University. Martin would live long enough to see what his father's solution had become, the foundation of the entire field of black hole physics. He died in 1997, 4 years after the Hubble Space Telescope had revealed the gravitational signature of supermassive black holes at the centers of galaxies. The story of what happened to Karl Schwarzschild's 1915 solution between the year it was derived and the year it was finally understood is one of the strangest in the history of physics. For decades after Schwarzschild's death, his solution was treated as a mathematical curiosity. Most physicists believed it described an impossible situation, the kind of compression required to produce a Schwarzschild radius. Squeezing a star to a sphere a few kilometers across was not believed to be physically achievable. Stars were thought to be stabilized by various pressure mechanisms, and no known mechanism could overcome those pressures completely. The mathematics described a valid geometry. The geometry was not believed to correspond to anything real. Einstein himself shared this skepticism. In 1939, he published a paper attempting to demonstrate that no physical object could ever be compressed below its Schwarzschild radius. Einstein argued, using a thought experiment involving a star made of particles in circular orbits, that as a star contracted toward its Schwarzschild radius, the orbital velocities required to support the star would exceed the speed of light. Since this was impossible, Einstein concluded, the compression itself must also be impossible. The Schwarzschild radius was a mathematical boundary that no physical process could actually reach. He was wrong. 2 months after Einstein's paper appeared, the American physicists J. Robert Oppenheimer and Hartland Snyder published a paper titled On Continued Gravitational Contraction. Oppenheimer and Snyder analyzed what would happen to a sufficiently massive, pressure-free dust cloud collapsing under its own gravity. The mathematics was unambiguous. The cloud would contract past its Schwarzschild radius and continue contracting toward a singularity at the center. From the perspective of a distant observer, the contraction would appear to slow as the surface approached the horizon, and the surface would asymptotically freeze at the boundary. From the perspective of an observer riding along with the collapsing matter, the contraction would proceed in finite, proper time, and the singularity would be reached. Oppenheimer and Snyder's paper appeared in Physical Review on September 1, 1939, the same day Germany invaded Poland and started the Second World War. Oppenheimer himself would soon be pulled away from black hole physics to lead the Manhattan Project. The paper was largely forgotten. The world had bigger problems. It would take another 25 years for the implications to be fully appreciated. The American physicist John Archibald Wheeler, who had collaborated with Einstein and Niels Bohr earlier in his career, returned to gravitational collapse in the early 1960s. Wheeler was a brilliant physicist and an even better namer. He gave the technical term geons to certain proposed self-gravitating electromagnetic objects. He coined the phrase wormhole for hypothetical space-time shortcuts. And in 1967, during a conference talk in New York, he popularized a name for the kind of object Schwarzschild's solution had been describing all along: black hole. The phrase had been used before, informally in scattered talks and articles, but Wheeler's adoption of it gave it permanence. By the early 1970s, black hole had become the standard term for any object dense enough to lie inside its own Schwarzschild radius. The mathematical structures Karl Schwarzschild had derived in a tent on the Russian front, the structures Oppenheimer and Snyder had shown, could actually form through gravitational collapse. The structures that Einstein had believed must be impossible finally had a name. And by then, the evidence was beginning to arrive. The first candidate black hole identified through observation was a binary star system called Cygnus X1, discovered as a strong source of X-rays by a sounding rocket in 1964. Cygnus X1 consists of a visible blue supergiant star and an invisible companion. The companion is massive, approximately 21 solar masses, but emits no light of its own. The X-rays come from material being torn off the visible star, accelerated to enormous velocities, and heated to millions of degrees as it spirals down toward the invisible object. The mass of the companion is too large for it to be a neutron star, the densest known kind of dead stellar remnant. It must be something more compact still. The only candidate, in the framework of general relativity, was a black hole. Stephen Hawking famously bet against the existence of black holes in Cygnus X1. In 1974, he wagered a 1-year subscription to Penthouse magazine against a 4-year subscription to Private Eye, betting that the object would turn out to be something other than a black hole. He intended the bet, he later wrote, as a form of insurance. If black holes turned out not to exist, at least he would have won the wager. He conceded the bet in 1990, having become convinced by the accumulating evidence that Cygnus X1 really was a black hole. By the 1990s, hundreds of stellar mass black holes had been catalogued in the Milky Way alone, identified through their X-ray emission, through the orbital motion of companion stars, or through gravitational lensing of background light. Supermassive black holes, millions or billions of solar masses, had been identified at the centers of nearly every large galaxy ever surveyed, through the observed motions of stars and gas in the central regions. The mathematical objects that Schwarzschild had derived in 1915 were no longer theoretical. They were ubiquitous. They were one of the most common kinds of astronomical objects in the known universe. Karl Schwarzschild was dead more than 70 years before the first observational confirmation that the objects his solution described actually existed. He never saw his name attached to the most extreme geometry in physics. He never knew that the formula he had mailed to Einstein from a tent in the Russian winter would become, over the course of the 20th century, the structural skeleton of one of the most disturbing predictions modern physics had ever made. What he left behind, in those weeks of work at the Russian front, was a formula that has since become the foundation of every black hole calculation in modern physics. The formula is this: the Schwarzschild radius of any mass equals 2 times the gravitational constant multiplied by the mass divided by the speed of light squared. In symbols, it reads as R sub s equals 2gm over c squared. In plain language, it says, take any object, a planet, a star, an asteroid, a human being, and compress it small enough, and there exists a critical radius at which the curvature of space-time around that object becomes so extreme that nothing, not even light, can escape from inside it. At the Schwarzschild radius of any mass, escape velocity reaches the speed of light. Beyond it, nothing causal can travel outward. That is the boundary, the event horizon. Let the numbers land. The Sun has a mass of approximately 2 times 10 to the 30th kilograms. Plug this into Schwarzschild's formula. The result is 2.95 kilometers. 2.95. If you took the Sun, with its current mass, 864,000 miles in diameter, more than 1 million Earths fitting inside, and compressed all of it into a sphere smaller than the city of San Francisco, that compressed Sun would become a black hole. Light could no longer escape from its surface. The boundary, the event horizon, would sit at 2.95 kilometers from the center. Earth has a mass of approximately 6 times 10 to the 24th kilograms. Schwarzschild's formula gives the result: 8.7 millimeters. If you compressed the entire Earth, every mountain, every ocean, every atom in the 7 sextillion tons of matter that makes up our planet, into a sphere smaller than a marble, you would have a black hole. The event horizon of that Earth mass black hole would fit inside a peanut shell. A typical stellar black hole formed from the collapsed core of a massive star has a mass of approximately 10 suns. Its event horizon, by Schwarzschild's formula, is about 29.5 kilometers across, the width of a mid-sized city, all the gravitational influence of 10 suns, concentrated into a region you could walk across in half an hour. If the Sun were replaced by a 10 solar mass black hole, Earth would continue orbiting it at exactly the same distance and exactly the same speed it currently orbits the Sun. We would only notice because the sky would be dark. A supermassive black hole at the center of a galaxy has a mass of millions or billions of suns. The supermassive black hole at the center of our own Milky Way, named Sagittarius A star, has a mass of about 4 million suns. Its event horizon is roughly 12 million kilometers across, about 30 times the distance from Earth to the Moon. The supermassive black hole at the center of the galaxy, M87, the one humanity first photographed in 2019, has a mass of 6.5 billion suns. Its event horizon is approximately 40 billion kilometers across, large enough that our entire solar system, including the orbit of Neptune, would fit inside it with vast room to spare. These numbers describe size. But what Schwarzschild's solution describes is not just a place, it is a time horizon. Here is what the mathematics says happens to time as something falls toward the event horizon. Imagine a clock falling into a black hole. The clock is sturdy and indestructible, a thought experiment, not a real device. From the perspective of a distant observer watching this clock through a telescope, something very strange happens. As the clock approaches the event horizon, its ticking slows. Not because the clock is broken, because time itself, at the position the clock is reaching, runs slower relative to time where the observer is standing. The slowing is gradual at first. At twice the Schwarzschild radius, the clock ticks at about 70% of the rate it would if it were sitting next to the observer. At 1.5 times the Schwarzschild radius, it ticks at about 58%. At 1.1 times the Schwarzschild radius, almost at the horizon, it ticks at about 30%. The closer it gets, the slower it ticks. And then, as the clock reaches the event horizon itself, something mathematically catastrophic happens. The ticking does not just slow, it stops. The math gives the answer infinity. The clock, from the distant observer's perspective, freezes forever. The image of the clock, made of light bouncing off its surface, also freezes. It dims, redshifts, and lingers, a fading, motionless ghost suspended just outside the event horizon. The observer can watch it for the rest of their lives. They can watch it for the rest of the universe. The clock will appear to remain at the horizon, ticking imperceptibly until the very end of time. The image will fade until it becomes too dim to see. But mathematically, it never quite crosses. It never quite enters. It is frozen at the boundary forever. This is not metaphor. This is what the equations of general relativity predict, and what has been verified by every observation we have ever made of matter falling toward an event horizon. The slowing is real. The freezing is real. From the outside, the event horizon is a place where time stops. And now the question that breaks the universe. What about from the inside? From the perspective of the clock itself, falling freely toward the event horizon, nothing dramatic happens at the boundary. The clock continues to tick at its normal rate. The observer who happens to be falling alongside the clock, also indestructible, also a thought experiment, will not notice anything as they cross the event horizon. They will not feel a wall. They will not see a barrier. They will continue falling toward the center of the black hole, and from their own perspective, time will continue to flow forward at 1 second per second. From outside, that observer is frozen at the horizon for eternity. From their own viewpoint, they have already crossed it. Both views are correct. Both are mathematically valid. Both are what general relativity predicts. So which one is true? The answer, when you sit with what Schwarzschild's equation actually says, is that the question itself contains a flaw. There is no master view. There is no objective answer about whether the clock has crossed the horizon. The two views are not just different perspectives on the same event. They are two genuinely incompatible accounts of what time even is. And inside the event horizon, time becomes something stranger still. So the question became, how? How can time be one thing for one observer and another thing for another observer, with no fact of the matter about which one is right? How can a clock be both frozen at the horizon and already past it, simultaneously, in the same universe? The answer requires confronting what time really is. In Newton's universe, time was a stage on which physics took place. Events happened against the background of time. Time was the river, and matter was the boats riding on its current. The river flowed at the same rate everywhere. The boats might travel faster or slower through space, but the current beneath them was universal. In Einstein's universe, time is not a background. Time is a dimension of the same fabric as space. The 4 dimensions, 3 of space and 1 of time, are woven together into a single geometric object called space-time. Mass and energy curve this fabric. The curvature is what we feel as gravity. A planet orbits a star because the star bends the space-time around it, and the planet follows the straightest possible path through the bent geometry. This is not a metaphor. It is a literal mathematical statement about the structure of reality. Time is geometric. Time is curved. Time at different positions in a gravitational field runs at different rates, not because the clocks at those positions are different, but because the underlying geometry of the universe at those positions is different. Once you accept this, the strange behavior at the event horizon starts to make sense. The reason a clock appears to freeze at the horizon from the outside is not that the clock is malfunctioning. It is that the space-time geometry between the outside observer and the horizon has been stretched so severely by the gravitational curvature that the path of any signal coming back out, the path of the light that the observer needs to see the clock, has become infinitely long. The clock is sending its information toward the observer, but the geometry between them has stretched so much that the information will never arrive. Not because the universe is hiding the information, because the universe, at this point in the geometry, contains an effectively infinite gap. Now we can ask what happens inside. For non-rotating black holes, the kind Schwarzschild solved, the answer is something that physicists spent decades refusing to accept. Inside the event horizon, the radial coordinate, which describes distance from the center, undergoes a mathematical change of role. Outside the horizon, the radial coordinate is space-like. It is just a direction. You can move toward the center or away from the center, the same way you can move east or west. Inside the horizon, the radial coordinate becomes time-like. It stops being a direction in space. It becomes a direction in time. What this means in practical terms is the most disturbing prediction in classical relativity. Inside the event horizon, you cannot avoid the singularity at the center any more than you can avoid tomorrow. Moving outward, moving back toward the horizon, back toward the rest of the universe, is no longer a choice you can make. It is no longer a direction that exists. The singularity at the center is not a place anymore. It is your future. It is, in a literal mathematical sense, the next moment in time for you, and the next, until you arrive there. The English mathematician Roger Penrose, working with Stephen Hawking in 1965 and again in 1970, proved that this is not a quirk of the Schwarzschild solution. It is a general feature of any black hole formed by gravitational collapse. The singularity is inevitable. The event horizon is inevitable. The inversion of space and time inside the horizon is inevitable. Penrose received the 2020 Nobel Prize in Physics for this work. Specifically, the Nobel Committee wrote, for the discovery that black hole formation is a robust prediction of the general theory of relativity. The singularity theorems, as they are now called, are among the most important results in 20th century physics. Penrose's 1965 paper, published in Physical Review Letters under the title Gravitational Collapse and Spacetime Singularities, showed mathematically that once a region of spacetime collapses to a certain critical density, the formation of a singularity at the center is a necessary consequence of the equations of general relativity. The formation does not depend on the symmetry of the collapse. It does not depend on the type of matter involved. It does not depend on the precise initial conditions. Singularities are not a quirk of idealized situations. They are, in the language of mathematical physics, generic outcomes of gravitational collapse. Stephen Hawking extended Penrose's work in the late 1960s. Together, in a sequence of papers published between 1970 and 1972, Hawking and Penrose proved a series of related theorems that applied not only to gravitational collapse, but to the universe as a whole. If general relativity is correct, and a century of experimental verification says it is, then singularities are inevitable features of any spacetime that contains gravitational collapse. They are inevitable at the center of every black hole. They are inevitable, by extension, at the moment of the Big Bang, when the entire observable universe was concentrated in an infinitesimal point of infinite density. The mathematics that describes the boundary at the event horizon and the mathematics that describes the boundary at the beginning of time are the same mathematics. The implications were almost intolerable to many physicists working in the field at the time. Singularities are mathematical absurdities. They are places where the equations break down, where physical quantities become infinite, where the universe stops being describable by the tools we have. To prove that they were not optional features of the theory, that they could not be eliminated by clever boundary conditions or careful initial setups, was to prove that general relativity contained, at its mathematical heart, a built-in failure mode. The theory predicted its own breakdown. This was the unsettling background against which the rest of black hole physics developed in the 1960s and 70s. In 1963, a New Zealand mathematician named Roy Kerr had derived another exact solution to Einstein's field equations, this one for a rotating mass. Schwarzschild had assumed his black hole was not spinning. Kerr removed that assumption. The resulting solution, now called the Kerr metric, describes the space-time geometry around a rotating black hole. It is significantly more complex than the Schwarzschild solution. It has two event horizons instead of one, an inner Cauchy horizon and an outer event horizon, and a region of space between them called the ergosphere, where space itself is being dragged around by the rotation of the central mass. An object inside the ergosphere cannot remain stationary relative to the distant stars. It must move with the rotation, swept along by the dragged spacetime. The phenomenon is called frame dragging, and it has been measured directly around Earth by satellites, including Gravity Probe B and the Italian LAIRS satellite. Real black holes almost certainly rotate. The collapsing stars that form them generally have angular momentum, which is conserved during the collapse. The resulting black hole inherits the spin of its progenitor, often spinning at a substantial fraction of the maximum rate the Kerr equations permit. Sagittarius A star, by current observations, rotates at roughly 10% of the theoretical maximum. M87 star rotates significantly faster, possibly approaching the upper limit. The black holes that exist throughout the universe are not Schwarzschild's idealized non-rotating spheres. They are Kerr's rotating geometries, with their dragged spacetime and their dual horizons and their richer internal structure. Between 1967 and 1975, a sequence of theorems by Werner Israel, Brandon Carter, Stephen Hawking, and David Robinson proved one of the most striking results in black hole physics. Any black hole formed by gravitational collapse, regardless of the complexity of the matter that formed it, settles down into a state that can be described by exactly three numbers: its mass, its electric charge, its angular momentum. Nothing else. The full state of a black hole is captured by three real numbers, and any additional information about how the black hole formed is lost beyond the event horizon. John Wheeler, who had named the black hole itself, summarized the result with another memorable phrase. Black holes, he said, have no hair. The no-hair theorem, as it is called, is one of the most extreme statements in physics. It says that a black hole formed from a collapsing star, a black hole formed from a collapsing galaxy core, a black hole formed by the merger of two smaller black holes, a black hole formed by any other mechanism whatsoever, all settle down into the same kind of geometric object, distinguishable only by three numbers. The history of the matter that formed them is gone. The information is sealed behind the event horizon, and there is, from outside, no way to retrieve it. Or there isn't, unless something else is going on. In 1974, Stephen Hawking published a paper that overturned what physicists thought they knew about black holes. The paper applied quantum field theory to the geometry around an event horizon. Hawking discovered something nobody had expected. Black holes are not entirely black. Quantum effects near the event horizon cause them to emit a faint glow of radiation, with a temperature inversely proportional to the mass of the black hole. The radiation is now called Hawking radiation. The mechanism is subtle. In quantum field theory, even empty space is not truly empty. It is a sea of fluctuating fields, with pairs of virtual particles continuously being created and annihilating themselves on timescales too brief to be directly observed. Near the event horizon of a black hole, these virtual pairs can be separated by the strong gravitational gradient. One member of the pair falls into the horizon, the other escapes. From the perspective of a distant observer, the black hole appears to be emitting particles. Over astronomical timescales, this emission carries energy away from the black hole, causing it to lose mass. For black holes of stellar mass, the effect is negligible. A solar mass black hole would take approximately 10 to the 67th power years to evaporate by Hawking radiation alone. That is a number 10 followed by 67 zeros. It is many trillions of times longer than the current age of the universe. For supermassive black holes, the timescales are even longer. The largest known black holes will outlast every star in the observable universe by enormous factors. But the effect exists. Black holes are not eternal. Given enough time, they will dissolve. The numbers here are worth slowing down on. The current age of the universe is approximately 13.8 billion years. That is the entire span of time since the Big Bang. The Sun has been burning for about 4.5 billion years, roughly a third of cosmic history. Stars like the Sun will continue forming for perhaps another 100 trillion years, after which the gas needed to make new stars will be exhausted. At about 100 trillion years from now, the last new star will be born. By a quadrillion years from now, all stars will have burned through their fuel and gone dark. The cosmos will be lit only by the slow infrared glow of cooling stellar corpses, white dwarfs cooling toward black dwarfs, neutron stars radiating their residual heat into a sky that is no longer dotted with living stars. This is the end of the stelliferous era. It ends, by current models, around 10 to the 14th years after the Big Bang. The universe will have lived through its first major epoch and entered its second. The second epoch is sometimes called the degenerate era. It is the era of stellar remnants. White dwarfs continue to cool. Neutron stars continue to spin down. Matter slowly drifts and gravitates and aggregates, with the ordinary processes of nuclear physics no longer driving change. Galaxies gradually disperse as their stars wander out into intergalactic space. Black holes continue to feed where matter remains to feed them, growing larger as nearby debris falls in. The degenerate era is expected to last roughly until 10 to the 40th years, when even protons, the most stable known particles in ordinary matter, may begin to decay. If protons are not truly stable, and current physics does not rule out a very slow decay process, then sometime in the next 10 to the 40th years, the last of the ordinary matter in the universe will dissolve into radiation. The white dwarfs and neutron stars will simply evaporate, particle by particle, into a thin background of photons and lighter leptons. What is left, when ordinary matter is gone, is black holes. The black hole era begins around 10 to the 40th years and lasts until 10 to the 100th years. For 60 orders of magnitude of time, a span that dwarfs the difference between a heartbeat and the current age of the universe, Black holes are the dominant structures in the cosmos. There are no stars. There is no ordinary matter. There is no light from fusion. The universe is dark, almost empty, and dotted with black holes that drift through enormous distances of space, slowly, patiently radiating themselves away into the cold of cosmic expansion. Solar mass black holes evaporate first, on timescales around 10 to the 67th power years. Supermassive black holes evaporate last. The black hole at the center of our galaxy, Sagittarius A star, with its 4 million solar masses, will take approximately 10 to the 87th power years to fully dissolve. The black hole at the center of M87, with its 6.5 billion solar masses, will take approximately 10 to the 100th power years, a number with 100 zeros after the 1. Beyond imagining, beyond the names humans have given to large numbers, it is simply the slowest decay process the laws of physics permit. Each black hole, during its long Hawking radiation lifetime, behaves the same way. It emits an exquisitely faint glow of thermal radiation. The radiation carries energy away, reducing the black hole's mass. As the mass decreases, the temperature of the radiation increases. At first, the process is almost imperceptibly slow. Then, as the black hole shrinks toward the end of its life, the radiation grows hotter and brighter. In the final fraction of a second, the remaining mass evaporates in a brief, bright burst of high-energy photons and particles. The event horizon, the boundary that for cosmic eras had held its grip on the matter inside, finally releases that matter back into a universe where nothing else remains to receive it. After the last black hole evaporates, there is nothing left. The universe enters its fourth and final epoch, sometimes called the dark era, in which only photons and stable lighter particles continue to drift through the endless expansion of space. There are no structures. There is no time in any meaningful sense, because there are no events. The universe simply continues to expand, growing colder and emptier forever, with nothing inside it doing anything anymore. The black hole era is the longest era. The dark era is the eternal one. What this means for our own moment is something almost too large to hold. We exist in the 1% of the 1% of the 1% of cosmic history. Stars are still being born. Galaxies are still bright with fusion. Earth is illuminated by a sun in the prime of its life. None of this lasts. None of this is the universe's typical state. The universe's typical state, the state it spends most of its existence in, is dark, cold, and mostly empty, with widely scattered black holes slowly dissolving into the void over time spans that have no human comparison. The event horizons we have photographed at M87 and Sagittarius A star will outlast almost everything else in the cosmos. They are not transient. They will not collapse. They will not vanish in any timescale a human mind can grasp. They will sit there, ringed by their dim photon halos, slowly evaporating for time spans that exceed the current age of the universe by factors of 10 to the 75th power or more. And inside each one, time, in the strangest sense, general relativity has ever asked us to mean it, has already stopped. This is the universe Schwarzschild's equations described. Not just the immediate strangeness of an event horizon, but the deep cosmic weight of it. The boundaries his math predicted are the last stable structures in physics. They will outlast every star, every planet, every memory of every civilization that ever existed. They will outlast the structures that gave rise to them. They will outlast even the names we have given them. The galaxies they sit in will disperse around them, leaving them isolated in vast, empty seas of cosmic darkness, alone with their frozen interiors, slowly bleeding out their mass over cosmic eras that have no end in human imagination. The implications of Hawking radiation for time, for information, and for the structure of the universe are still being worked out half a century later. If a black hole evaporates completely, what happens to all the information that was trapped behind its event horizon? The no-hair theorem says only three numbers, mass, charge, spin, describe the black hole. But the matter that fell in carried far more information than three numbers. Information about specific configurations of atoms, about the patterns of stars and gases that collapse to form the hole, about every photon that crossed the horizon during the hole's entire existence. If the hole evaporates into thermal radiation that depends only on its mass, that information appears to have been destroyed, and the destruction of information is forbidden by quantum mechanics. This is the black hole information paradox, and it has been one of the most active areas of theoretical physics for the past 50 years. The resolution, if there is one, is not yet established. Various proposals exist that the information escapes in subtle correlations between Hawking radiation particles, that it is encoded in the structure of the horizon itself, that the geometry of space-time near the horizon is fundamentally different from what classical relativity predicts. None of these proposals has been confirmed. The honest answer is that we do not know what happens to the information. We have equations that describe parts of the problem and a series of conjectures about how the parts might fit together, but no full theory. The mathematics that Karl Schwarzschild derived in a German artillery position on the Russian front in 1915 had, by the time Penrose proved his theorems half a century later, become the structural skeleton of one of the most disturbing predictions in physics. The event horizon is not a wall. It is not a surface. It is the boundary where the direction toward the center of the black hole stops being a place you can choose to go and becomes a moment in time you cannot avoid. This is where Einstein's space-time stops being a beautiful abstraction and starts being a horror story. What about the body of the observer crossing the horizon? What does it feel like to make this crossing? The popular answer involves a word that physicists half-jokingly coined in the 1970s: spaghettification. The mechanism is straightforward. A black hole's gravitational pull falls off with distance, like the gravity of any other mass. For a small black hole, say, a 10 solar mass stellar black hole, the gravitational difference between the head and the feet of a person falling feet first toward the event horizon becomes extreme well before the horizon is reached. The feet, being closer, are pulled harder than the head. The body stretches. The stretching grows worse as the person falls. Eventually, the gravitational gradient becomes large enough to overcome the molecular bonds holding the body together. The person is pulled into a long, thin filament, spaghettified. Long before any meaningful exploration of the interior could take place, the explorer would have been torn into a string of atoms. This is the version that makes it into textbooks and movies. It is real. It is what happens to anyone who falls into a stellar mass black hole. It is also misleading as a general claim about the experience of crossing an event horizon. For supermassive black holes, the kind that sit at the centers of galaxies, the gravitational gradient at the event horizon is much smaller. The horizon is much larger. The curvature of space-time over the length of a human body, near the horizon of Sagittarius A star, or M87, is gentle enough that the falling observer would feel essentially nothing. They would not be stretched at the boundary. They would not feel a tug. They would cross the event horizon and continue falling, with their wristwatch still ticking, with the stars behind them still visible, for a while, with their hand still in front of their face. They would notice nothing dramatic happening to them at the boundary itself. But everything about the universe outside the horizon, behind them, would now be unreachable, forever. Not in the sense that they could not return because they did not have a strong enough rocket. In the sense that back is no longer a direction that exists. The exit, the way home, the past, all gone, not blocked, erased from the structure of their available space-time. This is the deep weirdness of what Schwarzschild's equation revealed. The event horizon is not a wall in space. It is a one-way membrane in time. Things cross in. Nothing crosses out. Not because crossing out is hard. Because crossing out is no longer one of the directions the falling observer can move. The mathematics tells us one more thing. Something almost unbearable when you sit with it long enough. Inside the horizon, the singularity is the future. The falling observer is approaching not a place but a moment. The moment when their entire space-time ends. The moment when the geometry compresses to zero size. When the curvature becomes infinite. When the equations of general relativity break down. Because the answers they give are no longer finite numbers. The singularity is, in every meaningful sense, the end of time for the falling observer. Their future does not extend beyond it. There is no after. How much time do they have? For a stellar mass black hole, the answer is microseconds from horizon to singularity. For a supermassive black hole, Sagittarius A star, M87, the kind we have now photographed, the answer is longer. From the moment of crossing the event horizon of M87, a falling observer would have approximately 1 day before reaching the singularity. From the horizon of Sagittarius A star, about a minute. Brief, but finite. They could think a few last thoughts. They could look around. They could observe the increasingly extreme blue shift of the universe outside, compressed by the geometry into a brilliant point of light behind them. And then the singularity and the equations would end. This is what the equations of 1915 predict happens to anyone who crosses an event horizon. This is the mathematical heart of the event horizon's strangeness. It is not a wall. It is a time barrier disguised as a distance. If the theory is correct, the implications are not small. Now, consider what this means for us. We are not going to fall into a black hole. None of the reasonably sized black holes are close to Earth. The nearest known black hole, named Gaia BH1, sits about 1,500 light-years away in the constellation Ophiuchus. To reach its event horizon at any reasonable speed would take far longer than the human lifespan. The supermassive black hole at the center of our galaxy, Sagittarius A star, is 26,000 light-years away. Close enough on the cosmic scale to study, far enough that we will never visit it. But the time dilation effects of those distant black holes are not just theoretical. The same mathematics that predicts the freezing of clocks at the event horizon predicts a continuous gradient of time dilation extending outward from every black hole into the surrounding space, falling off with distance from the singularity. A planet orbiting close to a supermassive black hole would experience time dilation strong enough to skip years, decades, even centuries, relative to clocks in distant space, over the course of a single orbit. This is no longer abstract. It happens. Astronomers have observed stars orbiting Sagittarius A star at speeds approaching 3% of the speed of light on orbits that bring them within a few hundred AU of the event horizon, about 10 times the distance from the Sun to Neptune. The closest of these stars, named S02, completes its orbit every 16 years and has been tracked through more than a full orbital period since the early 1990s. The German astronomer Reinhard Genzel and the American astronomer Andrea Ghez shared the 2020 Nobel Prize in Physics, the same year as Penrose, for proving, through these stellar orbits, that the central object in our galaxy must be a supermassive black hole. The math worked. The orbits matched general relativity's predictions. The time dilation effects were measured directly. In May of 2018, S02 reached its closest approach to Sagittarius A star, what astronomers call pericenter, at a distance of about 120 astronomical units from the black hole. That is approximately 3 times the distance from Neptune to the Sun. At pericenter, S02 was moving at roughly 7,700 kilometers per second, about 2.5% of the speed of light. Genzel's team, working with the Very Large Telescope in Chile, Watch the star whip around the invisible center of our galaxy at this extreme velocity, and they measured the spectrum of light coming from it. The light was gravitationally redshifted by exactly the amount Einstein's equations predicted. The closest direct test of general relativity ever performed in a strong gravitational field, conducted on a star 26,000 light-years away, returned a result that matched the equations Karl Schwarzschild had derived a century earlier to within better than 1%. There is now a small library of these stars. Andrea Ghez and her team at UCLA have been tracking them since the early 1990s using adaptive optics on the Keck Observatory in Hawaii. Genzel and his team in Germany have done the same with the European Southern Observatory's telescopes in Chile. Together, the two teams have measured the orbits of more than 30 stars in the innermost few light-years around Sagittarius A star. The orbits trace a Keplerian ellipse around a single common focus. The focus is invisible. The mass at the focus is 4 million suns. There is no other object in physics consistent with these observations except a supermassive black hole. The closest the S-stars come to the event horizon of Sagittarius A star is roughly 1,400 Schwarzschild radii. They never approach the horizon directly. Their orbits are large enough that the time dilation factor at pericenter is measurable but modest, a fraction of a percent. But the existence of these orbits is the most direct confirmation we have that Schwarzschild's geometry describes real objects sitting at the centers of real galaxies. The mathematics of 1915, tested against the motion of stars whose light started its journey to Earth before the construction of the Egyptian pyramids, comes out right. For an observer aboard one of these stars, time would tick more slowly relative to clocks back on Earth. The effect is modest. These stars are not orbiting at the horizon, only near it, but it is measurable. The implication is direct. If you put a clock on a planet orbiting much closer to Sagittarius A star, the time dilation factor would grow. Approach the horizon, and the factor approaches infinity. There is one observation that goes further. The same year the German and American teams were sharing the Nobel Prize for tracking the S-stars, another instrument was looking even closer. The gravity interferometer, built by a European consortium led by the same Reinhard Genzel who tracked S02, sits at the European Southern Observatory's Paranal site in Chile. It combines the light from 4 auxiliary telescopes, each 1.8 meters in diameter, or alternatively, from 4 unit telescopes of 8 meters, into a single coherent measurement of astonishing precision. The instrument is sensitive to angles of approximately 10 microseconds, the same kind of resolution as the Event Horizon telescope, but at infrared wavelengths instead of radio, and from a single observatory site instead of a planet-wide array. On 3 nights in 2018, May 27th, July 22nd, and July 28th, gravity caught something it had been built to look for. Sagittarius A star was flaring. The flares lasted roughly 30 minutes each. Their infrared brightness rose to approximately the same level as the star S02. And as gravity tracked the position of each flare across the sky, the position moved. The flares were not coming from a fixed point. They were coming from a hotspot of gas, moving in a circle, orbiting around the black hole. The July 22nd flare made a partial loop in roughly 30 minutes. The hotspot, a clump of plasma heated to extreme temperatures by magnetic reconnection near the event horizon, was orbiting at approximately 30% of the speed of light on a circular path located between 7 and 10 gravitational radii from the center. In the language of black hole physics, that is just outside the innermost stable circular orbit, the closest any persistent matter can orbit without spiraling irresistibly inward. The Schwarzschild radius of Sagittarius A star, measured in the same units, is approximately 10 microseconds, and gravity tracked these orbits to within about 2 gravitational radii of accuracy. This is what it looks like when matter orbits within shouting distance of the boundary where time stops. The hotspot circled the black hole at a substantial fraction of the speed of light. Its position rotated through tens of microseconds of sky over the course of half an hour. The polarization of the light it emitted rotated through 180 degrees over the course of the flare, exactly the rotation pattern predicted for synchrotron radiation from charged particles spiraling along a magnetic field anchored at the event horizon. The motion matched the predictions of general relativity for circular orbits in a Kerr geometry around a 4 million solar mass black hole, exactly the kind of object Schwarzschild's mathematics had predicted in 1915. For the hot spot itself, time was running at a noticeably different rate than for the observers in Chile watching it. The gravitational time dilation at the innermost stable orbit of a black hole like Sagittarius A star is significant. For matter at that distance, time runs at roughly half the rate it does in the distant universe. For 30 minutes of observation on Earth, the hot spot experienced perhaps half that, 15 Earth minutes of its own local time, ticked out against the steeper part of the gravitational gradient. The matter was being pulled across the gradient as it orbited. Its clock was lagging behind the clocks of Chile. We watched, in real time, in our own infrared sensors, the local time of matter at the innermost stable orbit of a supermassive black hole. The deeper implication is what happens to that matter next. Material orbiting close to a black hole at relativistic speeds does not stay there indefinitely. The orbits at and below the innermost stable circular orbit are unstable. Matter near the boundary spirals slowly inward, releasing gravitational potential energy as it falls. The energy is radiated outward as electromagnetic emission across a vast range of wavelengths: radio, infrared, optical, ultraviolet, X-ray, gamma ray. The accretion disk around a feeding supermassive black hole is one of the most efficient energy conversion mechanisms in the universe. Up to 10% of the rest mass of accreted material can be converted into radiation. Nuclear fusion, by comparison, converts less than 1% of mass into energy. Black hole accretion is, gram for gram, an order of magnitude more efficient than the cores of stars. This is why quasars are the brightest persistent objects in the universe. A quasar is the visible signature of a supermassive black hole somewhere in a distant galaxy, in the process of swallowing large quantities of matter. The infalling material forms an accretion disk that emits across the electromagnetic spectrum, glowing at luminosities equivalent to the total light output of hundreds or thousands of normal galaxies. The most luminous known quasars outshine the entire Milky Way by factors of 10,000 or more. Some of them are visible from over 13 billion light-years away, which means the light we collect from them today set out toward us when the universe was less than 1 billion years old. We are looking, in effect, at the local time of matter being drawn toward event horizons in the early universe, with the time-dilated emission stretched out over 13 billion years of travel through expanding space before reaching our telescopes. When astronomers measure the spectrum of a quasar's accretion disk, they can read the gravitational time dilation directly from the data. Spectral emission lines from atoms in the innermost regions of the disk are redshifted relative to lines from the outer regions by amounts that match general relativity's predictions for matter orbiting at progressively smaller fractions of the Schwarzschild radius. The redshift is a direct measurement of the gradient of time in the immediate vicinity of an event horizon. Light leaving the inner accretion disk of a quasar takes 13 billion years to reach Earth, but the local time of the matter emitting that light was already running noticeably slow when the light departed, slowed by the gravity it was falling into. Some of that accreting matter never reaches the horizon. A fraction is launched outward instead, in narrow, fiercely collimated jets that extend for thousands of light-years beyond the host galaxy. The jet of M87, the same black hole the Event Horizon Telescope photographed, stretches approximately 5,000 light-years from the galactic center, a thin, bright spike of relativistic particles streaming outward at speeds approaching the speed of light. The jet is anchored at the event horizon. The energy that powers it comes from the rotation of the black hole itself, from the dragged spacetime of the Kerr metric, from the spin of the central object that Roy Kerr's 1963 solution had predicted would behave exactly this way. We have, in other words, multiple independent observational confirmations of the time dilation predictions of general relativity made at progressively shorter distances from black hole event horizons. The GPS satellites overhead, the atomic clocks in Boulder, Colorado, the S-stars at thousands of Schwarzschild radii, the gravity hotspots at 7 to 10 gravitational radii, the accretion disks of quasars at the innermost stable orbit, and, at the horizon itself, the red-shifted photon ring photographed by the Event Horizon Telescope, where the time dilation finally becomes infinite and the geometry of space-time closes itself off from the rest of the universe. This is the universe Karl Schwarzschild's equations described, the mathematics of 1915, derived in a tent on the Russian front by a 41-year-old astronomer calculating ballistic trajectories for German artillery, has been tested by every instrument modern physics has built to test it, at every scale from the centimeter-tall optical lattice clocks at NIST to the supermassive black holes 13 billion light-years away that powered the early universe's most luminous quasars. Every test has matched. The most dramatic dramatization of this is a movie that, by accident, became one of the most scientifically accurate explorations of relativistic time in mainstream cinema. The film is Interstellar, released in 2014. Its science consultant was Kip Thorne, a Caltech physicist who would 3 years later share the 2017 Nobel Prize in Physics for the LIGO collaboration's first direct detection of gravitational waves, a detection that itself was the most definitive proof yet that Einstein's general relativity is correct, and that black holes really exist with the properties he predicted. The LIGO detection is worth dwelling on. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. It consists of 2 enormous L-shaped detectors, one in Hanford, Washington, and one in Livingston, Louisiana, each with arms 4 kilometers long. Inside each arm, a laser beam bounces between mirrors at the ends of the L, measuring the precise length of the arms to a precision of 1/10,000th of the width of a proton. The detectors are designed to register the passage of gravitational waves, ripples in the fabric of spacetime predicted by Einstein in 1916, by the tiny stretching and squeezing they produce in the 4-kilometer arms. On September 14, 2015, at 9:50 in the morning Universal Time, both LIGO detectors registered a signal. The signal lasted for approximately 0.2 of a second. It had a characteristic shape, a chirp, rising in frequency and amplitude before terminating in a sharp ringdown. The signal arrived at the Livingston detector 7 milliseconds before the Hanford detector, exactly consistent with the time it would take a gravitational wave to travel between the 2 sites at the speed of light. The teams spent 5 months verifying the signal before announcing it publicly. When they did on February 11, 2016, they confirmed what the signal had revealed. It was the gravitational wave from the merger of 2 black holes. One had a mass of approximately 36 suns. The other, 29. They had been orbiting each other for billions of years, gradually losing energy to gravitational radiation, spiraling closer together over time, until at some point, 1.33 billion years ago, they finally collided and merged into a single black hole of approximately 62 solar masses. The remaining 3 solar masses of energy were converted into a single brief burst of gravitational waves that traveled outward from the collision at the speed of light, eventually passing through Earth 1.33 billion years after they were emitted. For a fraction of a second during the collision, the gravitational waves carried more power than all the visible light from all the stars in the observable universe combined. None of that power was visible. None of it was electromagnetic. It was carried entirely in the curvature of space-time itself, stretching and squeezing the fabric of the universe as the wave passed. LIGO measured it. The mirrors at the ends of the 4-kilometer arms moved by approximately 10 to the negative 18th meters, 1,000th the width of a proton. The Hanford and Livingston detectors registered identical signals. The teams used numerical relativity simulations to extract the masses, the spins, and the distance to the source. The merger had taken place 1 3/10 billion light-years from Earth. The signal had been traveling through space for 1 3/10 billion years before reaching the detectors. When it arrived, it lasted 2/10 of a second. The detection won the 2017 Nobel Prize in Physics, shared by Kip Thorne, Rainer Weiss, and Barry Barish. By the time LIGO announced the detection, the collaboration had also seen evidence of other mergers. Today, almost a decade later, more than 200 black hole and neutron star mergers have been recorded. The detectors observe a new one every few days. They have become a routine astronomical instrument, like a telescope that watches the vibrations of space-time itself. What LIGO confirmed, in a single 2/10 of a second signal, was every major prediction Einstein's general relativity had made about black holes. The two pre-merger objects had Schwarzschild geometries. The merger followed the curves Einstein's field equations predicted for the final in spiral. The post-merger object settled into a Kerr geometry, the rotating black hole solution that Roy Kerr had derived in 1963. The frequency of the ringdown, the brief oscillation as the new black hole reached its final state, matched the predictions of the no-hair theorem. Schwarzschild was right. Kerr was right. Hawking and Penrose were right. Einstein was right. The mathematics derived in fragments across the 20th century by men working in tents on the Eastern Front and patent offices in Bern and small offices at universities scattered across the world all came together in 2/10 of a second of space-time ripples, registered by mirrors moving 1,000th the width of a proton in two L-shaped buildings in the American South. For the movie, Thorne calculated the physics. The film depicts a planet called Miller's Planet orbiting a maximally rotating supermassive black hole called Gargantua. On Miller's Planet, 1 hour equals 7 years for the crew waiting in orbit above, a ratio of 1 to 60,000. When the surface team returns to the orbiting ship after a brief mission, they discover that 23 years and 4 months have passed for the astronaut who stayed behind. The math is real. The ratio is physically permitted by general relativity. To get a time dilation factor of 60,000 requires Miller's Planet to orbit extremely close to a black hole that is rotating very nearly at the theoretical maximum, what physicists call extremal Kerr. Real black holes likely cannot quite reach extremal Kerr because the physics of accretion limits the spin. But near-extremal black holes are not impossible, and the time dilation around them, while perhaps not exactly 60,000 to 1, is still extreme. A factor of 1,000, 10,000, perhaps 100,000 real planets orbiting real supermassive black holes somewhere in the universe right now are experiencing time at rates radically different from ours. This is the deeper implication of Schwarzschild's 1915 mathematics. Time is not a thing the universe has. Time is a thing the universe does. And the universe does time differently in different places. The rate at which time flows is determined by the local geometry of spacetime, which is determined by the mass and energy in the local region, which means there is no master clock against which all events take place. The second on your wrist, the second in your kitchen 1 floor below you, the second on Mars, the second in the atmosphere of a hot Jupiter exoplanet orbiting close to its star, the second near the event horizon of M87, the second at the horizon itself. These are all genuinely different seconds, local time at every position, a vast, continuous, varying landscape of clock rates spread across the entire cosmos. No reference point, no background, no absolute time. This is the universe Karl Schwarzschild's equations described, the universe Einstein's geometry implied, the universe Roger Penrose and Stephen Hawking proved was inevitable. We do not just live in this universe. We are this universe. Every second any of us has ever experienced has been a local second, ticked out against the local geometry of space-time at our specific position in the gravitational landscape of the cosmos. And then there is the question that even the implications layer cannot quite answer. if time inside the event horizon is no longer a coordinate, no longer a direction, no longer the smooth forward flow we are accustomed to, what is it? The equations tell us that inside the horizon, the radial coordinate becomes timelike. They tell us the singularity becomes the inevitable future of any falling observer. They tell us that the geometry, in the strict mathematical sense, performs an inversion of space and time roles. But they do not tell us what time is inside the horizon. The labels are mathematical conveniences. The reality they describe is something the words of human language have never had to handle before. Some physicists argue that time, in any meaningful sense, simply ends at the singularity. The equations break down there. Quantum gravity, whatever it turns out to be, would presumably take over at the smallest scales near the singularity, and the smooth, classical geometry of relativity is not the right description anymore. There might be no inside the singularity at all. The honest answer is that we do not know what happens. We have equations that work all the way down to the singularity and then stop. Beyond that, modern physics has hypotheses and proposals: string theory, loop quantum gravity, holographic principles, but no consensus, no verified prediction, no instrument capable of testing what really happens. What we have is the certainty that time on the way down behaves in ways that should be impossible. The clock from outside freezes at the horizon. The clock from inside continues falling toward a future that is no longer a time but a place, and a place that is no longer a place but a time. The two accounts are both right. Both are what the universe really does. And the universe, evidently, is comfortable with what to a human mind looks like a contradiction. The Italian physicist Carlo Rovelli has spent much of his career arguing that this is not a contradiction at all. It is, he writes, evidence that time as we ordinarily conceive of it, a single, universal, smoothly flowing river, is an illusion. What the universe really contains is local geometry, local clock rates, local sequences of events. The now we feel ourselves to inhabit is a feature of our particular position in the cosmic landscape, not a property of the cosmos as a whole. There is no cosmic now. There is no universal moment. The event horizon is merely the place where this fact, which is always true everywhere, becomes impossible to ignore. If Rovelli and the relational physicists are right, then time inside the event horizon is not strange because the universe is broken there. It is strange because the universe was always like that, and the horizon is just the first place where the strangeness reaches a scale that we cannot pretend away. We will not be able to resolve this with any of the experiments we currently know how to perform. Information cannot escape the horizon, by definition. Whatever happens inside, whatever time becomes, whatever space becomes, whatever the singularity actually is, in the most literal sense, beyond our ability to observe. The honest answer to what time means inside a black hole is that we have the mathematics. And the mathematics gives us answers that do not translate into the words of any human language. And the experiments that would let us check are forbidden by the geometry itself. And there is one more piece to this that almost nobody talks about. We have a photograph. Two of them, in fact. On April 10th, 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's event horizon. The black hole in question was Métis 7 star, the supermassive black hole at the center of the elliptical galaxy Messier 87, located 53 million light-years from Earth. Its mass, 6.5 billion times the mass of the Sun. Its event horizon, roughly 40 billion kilometers across. The image showed an orange-red ring of glowing plasma surrounding a dark central region, the silhouette of the event horizon itself, the boundary inside which not even light can escape. On May 12, 2022, The same collaboration released a second image. This one was of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. 4.3 million solar masses, 26,000 light-years from Earth. The image, again, showed a ring of light surrounding a central dark region. The two images, despite being taken of black holes that differ in mass by more than 1,000-fold, look remarkably similar. The reason is that general relativity governs the geometry close to the horizon, and the geometry of any black hole is essentially scale invariant. A black hole is a black hole. What very few people understand about these images is what they actually contain. The Event Horizon Telescope is not a single instrument. It is a network of radio observatories spread across the planet, synchronized so precisely that they can be combined into a single virtual telescope as wide as the Earth itself. The collaboration includes 8 observing stations: the Atacama Large Millimeter Array in Chile, the South Pole Telescope at the geographic South Pole, the IRAM 30-meter telescope in Spain, the Sub-Millimeter Telescope in Arizona, the Sub-Millimeter Array on Mauna Kea in Hawaii, the James Clerk Maxwell Telescope, also on Mauna Kea, the Large Millimeter Telescope in Mexico, and the IRAM Noema Observatory in France. Each of these stations carries an atomic clock, the same kind of clock, accurate to nanoseconds, that the GPS satellites use overhead. The clocks are kept in sync across continents so that the radio signals captured by each station can be correlated against each other to picosecond accuracy. In April of 2017, all 8 stations observed both M87 and Sagittarius A star simultaneously at a wavelength of 1.3 millimeters. The data produced was enormous. Each station recorded petabytes of raw radio measurements. The total data set was too large to transmit over the internet. Instead, the data was stored on physical hard drives, about 1,000 kilograms of them, and physically shipped to 2 correlation centers, the MIT Haystack Observatory in Massachusetts and the Max Planck Institute for Radio Astronomy in Bonn, Germany. There, supercomputers spent 2 years processing the signals, combining them through a technique called very long baseline interferometry until a single coherent image emerged. The image has an angular resolution of approximately 20 microarcseconds. This is the smallest angle a telescope can resolve. To put this in human terms, 20 microarcseconds is the angle subtended by a donut on the surface of the Moon as seen from Earth. The Event Horizon Telescope has the resolution to read the headline of a newspaper on the surface of the Moon. 300 researchers, 60 institutions, more than 20 countries, and a planet-size virtual telescope were assembled to make this single picture. What the picture shows is not what most people think it shows. The image is not a snapshot. It is a time collage. The bright ring of light surrounding the dark central region is the photon ring, light that orbited the black hole 1 or more times before escaping outward toward the telescope. The strong gravity of the black hole bends the paths of photons that pass close to the horizon. Some photons pass once and continue on. Some loop around once before escaping. Some loop around twice. Some loop around 3 times, or 4 or more. The geometry near a non-rotating black hole produces a thin, sharp feature called the photon sphere, located at 1.5 times the Schwarzschild radius, where light can theoretically orbit in a closed circle. Photons that pass slightly outside the photon sphere can loop around the black hole an arbitrary number of times before escaping. The physics of the photon sphere is worth sitting with. At 1.5 times the Schwarzschild radius, at exactly that distance from the singularity, no closer, no further, the curvature of space-time is precisely the curvature required for a photon to orbit in a stable, closed circle. Light, normally the straightest thing in the universe, follows the curvature of space-time so completely that, at this specific distance, the curvature wraps the photon's path back on itself. The photon could, in principle, orbit forever, completing circle after circle around the black hole without escaping and without falling in. In practice, the orbit is unstable. A photon traveling at exactly the photon sphere distance, on exactly the right trajectory, would orbit indefinitely. A photon a hair too far inside falls toward the singularity. A photon a hair too far outside spirals outward and escapes. The photon sphere is a knife's edge of geometric balance, where the gravitational curvature exactly matches the inertia of light itself. For a black hole the mass of M87, the photon sphere sits at approximately 60 billion kilometers from the center, about 4 times the diameter of Pluto's orbit. The orbital period of a photon at this distance, calculated from the Kerr geometry of M87, is approximately 5 days. A photon caught at exactly the photon sphere distance would, in 5 days of its own travel, complete a full lap around a black hole 40 billion kilometers wide, then start the second lap, then the third, then the fourth, until either some tiny perturbation knocked it free or some equally tiny perturbation sent it falling in. What this means for the Event Horizon Telescope images is precise and disturbing. The bright photon ring in the M87 photograph contains light that did exactly this. Some of the photons in that ring took a single pass past the photon sphere before escaping. Some looped once, some looped twice, some looped 3 or 4 or 5 times. The image we see is the integrated light of all these different photon paths, all of them sourced from the matter swirling around the black hole at different moments in the recent past. The mathematician Samuel Graller, working with Daniel Holtz and Robert Wald at the University of Chicago in 2019, calculated that the photon ring observed by the Event Horizon Telescope can actually be decomposed into a series of nested subrings. The first subring contains photons that took the direct path. The second subring, slightly thinner and slightly inside the first, contains photons that loop the black hole exactly once. The third subring, thinner still and further inside, contains photons that looped exactly twice, and so on, all the way down to a theoretical infinity of progressively thinner subrings approaching the location of the photon sphere itself. Each subring contains light from progressively earlier moments in the history of the black hole's accretion disk. The current Event Horizon Telescope cannot resolve these subrings individually. Future versions of the telescope might. There are proposals to extend the array to include observatories in low Earth orbit and on the surface of the Moon, which would expand the virtual baseline from the diameter of Earth to multiple Earth radii or beyond, and would correspondingly improve the angular resolution. A space-based EHT would, in principle, be able to resolve the second and possibly third subring directly, allowing astronomers to literally look at photographs of black holes assembled from light, captured by photons that orbited the event horizon 2 or 3 times before escaping toward Earth. Each subring would be a photograph of the black hole as it existed days, weeks, months, or years before the snapshot. This is the photograph the universe takes of itself when light gets caught in the curvature of space-time. Time, smeared across the gravitational geometry, captured in a donut-shaped collage. Each loop adds to the photon's path length. Each loop adds to the time the photon spent traveling. The light that arrives at the telescope after looping the black hole 3 times left its emitting source much earlier than the light that arrived after a single direct path. Each pixel of the ring in the EHT image is a composite of photons that traveled paths of different lengths and therefore took different amounts of time to arrive. The image is not what M87 looks like right now. The image is what M87 looks like across a range of moments, layered together by the geometry of the black hole's gravity. In some sense, every photograph is a time collage. Light from a distant lamp in your room reaches your eye a few nanoseconds after it left the lamp. Light from the sun reaches Earth 8 minutes after it left the sun's surface. Light from the most distant galaxies in the universe reaches our telescopes after journeys of more than 13 billion years. But the time spread in those photographs is usually small relative to the timescale of the objects involved. A 9-minute delay does not matter much when photographing a solar flare that evolves over hours. The time spread in the Event Horizon Telescope images is different. The geometry of the black hole concentrates the light into a thin photon ring, and the photons in that ring come from a range of different times, separated by hours, days, possibly years, but blended into a single image. We are looking at M87, not as it existed at a single moment, but as it existed across many moments. The picture is a smear in time, focused by the gravitational lens of the black hole itself into the appearance of a single still photograph. And so we arrive at something that should be impossible. We have photographed the place where time stops. Not metaphorically, literally. The dark region at the center of the EHT image is the event horizon, the boundary inside which time, as observed from outside, no longer flows. The bright ring around it is light that orbited that boundary, at the place where the gravity is just barely weak enough for photons to escape, blended together from many different moments by the geometry. The image is the first photograph in human history of a region of spacetime where the relativistic prediction of frozen time becomes directly visible. In March of 2021, the Event Horizon Telescope collaboration released a follow-up analysis of the M87 data. The new analysis showed the same ring of light, but with additional information extracted from the polarization of the radiation. Polarization is a property of light related to the direction of its electromagnetic oscillations. The polarization pattern around M87 traces the magnetic field structure in the plasma orbiting the black hole. The pattern showed a spiraling magnetic field, anchored at the photon sphere, threading outward into the surrounding accretion disk. This is the magnetic structure that launches the jet of relativistic particles that extends from M87 for thousands of light years. The jet itself is observable from Earth with optical telescopes. The Hubble Space Telescope has imaged it many times. It extends approximately 5,000 light-years from the center of M87, a thin, bright spike of electromagnetic radiation streaming outward at speeds approaching the speed of light. The base of the jet is anchored at the event horizon. The energy that powers it comes from the rotation of the black hole itself, the same rotation that gives the Kerr metric its peculiar geometry, the same rotation that drags spacetime around the horizon. What we now know, after the Event Horizon Telescope images and the LIGO detections and the S-star observations, is that black holes are not theoretical curiosities. They are not mathematical edge cases. They are common, abundant, ubiquitous astronomical objects, sitting at the centers of nearly every galaxy in the observable universe, anchoring the structure of those galaxies through their gravitational influence, launching jets that extend across thousands of light-years, and warping time in their vicinity by exactly the amount the equations of 1915 predicted. Most people who see the image see a donut. Most articles about the image describe it as a donut. The reality is more disturbing. We are looking at a hole in the universe where time, in the local frame of the falling observer, comes to an end. We are looking at the boundary that Karl Schwarzschild's equation predicted in 1915, derived in a tent on the Russian front of the First World War, never seen by him, never imagined as a real photographable object by anyone before the late 1960s, when Penrose and Hawking proved that such objects must exist. We are looking, in those two photographs, at the place where the most disturbing prediction in modern physics becomes a verified observational fact. We did not photograph a black hole. We photographed where time ends. And there is one more thing about these two photographs worth holding in mind before we let them go. What we have captured is not what is inside. What we have captured is what is outside. The bright ring is the light that escaped. The dark center is not a picture of the interior. It is a picture of nothing, because no light from inside the event horizon can ever reach us. Whatever is happening past that boundary, whatever the matter that fell in is doing, whatever shape the space-time takes, whatever the singularity at the center actually looks like, None of it can be photographed. Not now. Not in 10,000 years. Not in any future a human civilization can dream of building toward. The information is locked behind the geometry, and the geometry forbids any light, any signal, any particle from emerging to be recorded by any instrument we will ever build. The Event Horizon Telescope photographs are the boundary of the photographable universe. They are, in the most literal sense, the absolute limit of what cameras can see. Everything brighter than the horizon, everything outside that ring, is in principle accessible to telescopes. Everything inside is, by the laws of physics themselves, permanently sealed off. This is not a limitation we will solve with bigger arrays or sharper sensors. It is not a quirk of current technology. It is built into the structure of space-time. The event horizon defines what is forever beyond observation. Everything we will ever know about the interior of a black hole, we will know from mathematics, from the equations Karl Schwarzschild solved in the trenches of 1915, from the singularity theorems Penrose proved in the 1960s, from the simulations that quantum gravity researchers run today on supercomputers that still cannot quite reach the answer. The interior is the universe's permanent secret. There are perhaps 100 million black holes in the Milky Way galaxy alone. Across the observable universe, there are roughly 40 quintillion. Each one is a small region of space-time that has decided to keep its interior to itself. Each one is a tiny patch of cosmos that no observation can ever penetrate. Together, they sit scattered across the void, billions of light years apart from one another, each holding its own permanently sealed contents, each ringed by its own faint glow of light that was almost but not quite captured. What we have, instead, is the picture of the threshold. Not the place itself, but the door. Not the room beyond, but the frame around it. And inside that frame, at the center of the photograph, in the dark patch the camera could not enter, is the only kind of structure in the cosmos that has decided to keep its contents to itself forever. Now come back slowly to your own clock. The second hand of your watch is still moving. It is moving at 1 second per second from your own perspective. It is also simultaneously moving slightly slower than the GPS clocks orbiting 20,000 kilometers above you. It is moving slightly slower than identical clocks at higher altitudes. It is moving slightly faster than identical clocks at lower altitudes. The kitchen, 1 floor below you, contains a slightly slower clock than your bedroom 1 floor above. The difference, at the scale of a human life, is nanoseconds. But the difference is real. The difference is measurable. The difference is the same kind of difference that, at the event horizon of a supermassive black hole, becomes infinite. You are part of a continuous gradient of time. Every point in the universe has its own local clock rate, set by the local gravitational geometry. The clock on your wrist sits on a vast, sloping landscape that extends outward through the atmosphere, through low Earth orbit, through the orbit of the Moon, through the rest of the solar system, through the Milky Way, all the way to the event horizons of black holes near and far. The slope is gentle near you. The slope steepens near massive objects. The slope becomes vertical at the event horizon itself, where a clock falling in is, from your perspective, frozen forever. There is no master clock. There is no universal moment. There is no cosmic now against which all events take place. There is only the continuous landscape of local times, smoothly varying across the geometry of space-time, more or less slow depending on where you happen to be standing. The event horizon is not a special place. It is the place where the gradient finally completes itself. You are a slow ticking clock in a universe of slow ticking clocks, each one running at its own rate, each one measured only against the local geometry of where it sits. The watch on your wrist is part of this. The atoms in your body are part of this. The thoughts you are having as you listen to this, the rate at which you are forming them, the rhythm of your breathing, the slow heart in your chest, all of it is being measured by local time against the curvature of the space-time you happen to occupy on this particular planet in this particular galaxy. The event horizon is the place where one such clock would finally stop. Yours has not. You are still here. Think about what it would have looked like to Karl Schwarzschild if he could have seen any of this. He died in 1916, before the radio telescope was invented, before the first satellite was launched, before atomic clocks existed, before relativity had been confirmed by any experiment beyond the bending of starlight near the sun, before quantum mechanics had been fully formulated. He died in his early 40s in a hospital in Potsdam, with a disease that modern medicine can now treat, having spent the final months of his life unable to write or speak clearly because of the blisters on his skin and mouth. He died believing his solution was a mathematical curiosity, a piece of clean derivation he had been pleased to produce, but with no clear application to the physical universe. He had no idea that the formula would, over the next century, be carved into the foundation of one of the most active fields of physics in human history. He had no idea that 100 years after his death, a global collaboration of 300 scientists would assemble a planet-sized telescope to take a photograph of the boundary his formula had defined. He had no idea that the same year his solution was rediscovered by the world, gravitational waves from two colliding versions of his geometry would be detected by laser interferometers 4 kilometers long. What we have, that he did not have, is the full picture. We can see what his equation meant. We can photograph the boundaries it predicted. We can measure the time dilation effects it implied. We can listen to the gravitational ringdowns of merging Kerr black holes and verify that the resulting geometries are exactly the geometries general relativity predicts they should be. We live inside the universe he glimpsed for the first time from a tent on the Russian front in the winter of 1915. You exist inside this universe right now. The watch on your wrist is part of this universe. The clocks on the GPS satellites overhead are part of this universe. The photons looping around M87 star and Sagittarius A star are part of this universe. The stars orbiting Sagittarius A star at 3% of the speed of light are part of this universe. The two colliding black holes whose merger LIGO detected on September 14, 2015, are part of this universe. The not quite extremal Kerr black holes around which planets like Miller's planet might really be orbiting somewhere in the night sky are part of this universe. You are part of this universe. You can feel time differently. You always could. The pull of a long afternoon, the compression of a year you barely remember, the slow heaviness of grief, the vanishing speed of a happy day. That isn't just psychology. That is, in the deepest sense, the equations of general relativity have ever allowed us to mean it. Physics, scaled to your own modest gravity, scaled to your own local geometry. The universe lets time bend everywhere, all the time, in ways most people never notice because the bending is small. But the bending is real. And the same equations that bend your time so gently are the equations that, somewhere out there, at the edge of a supermassive black hole, 40 billion kilometers across, bring time to a complete stop. The mathematics that Karl Schwarzschild derived in a tent on the Russian front in the winter of 1915, the mathematics that he mailed to Einstein 6 days before he himself would be invalided home with the disease that killed him, the mathematics that has been verified by atomic clocks, by GPS satellites, by stellar orbits, by the gravitational waves from colliding black holes, by the photons that looped around M87 and Sagittarius A star before reaching the largest telescope humanity has ever built. that mathematics describes the world you are living in right now. Time is not what you were told it was. It bends. It stretches. It slows. It can, at the right place, in the right geometry, stop entirely. You are sitting in the part of the gradient where time runs gently, smoothly. Almost, but not quite, at the rate it does in empty space. Your clock and the clock of someone you loved who has already died are not on the same place in the gradient anymore. Your clock and the clock of someone who has not yet been born are not on the same place in the gradient yet. Your clock is yours alone, ticking at the rate the universe permits it to tick, in this exact place, at this exact moment in the geometry. There is no clock that ticks the same way for everyone. There is only the slow, continuous landscape of all the local times the universe keeps in parallel, with no master clock to bind them together, no cosmic now to anchor them, no privileged frame against which all of them could be measured. This is the universe that Karl Schwarzschild's mathematics revealed in 1915. This is the universe Einstein's geometry implied. This is the universe Roger Penrose and Stephen Hawking proved was inevitable. This is the universe the Event Horizon Telescope photographed. This is the universe you are sitting in right now, listening to this with the watch on your wrist still moving at the rate the geometry permits, with the second hand going around at the rate determined by the curvature of space-time in your room. The event horizon is the place where this gradient finally reaches its conclusion, where the slowing finally becomes infinite, where the local time finally stops keeping pace with anything outside, and the clock falls in and freezes there, frozen at the boundary as a faint, red-shifted ghost, forever. But that is somewhere else, somewhere far away, somewhere 53 million light-years from your bed, or 26,000 light-years, or 1,500 light-years for the nearest known black hole, or who knows how many light-years for the smaller stellar black holes nobody has detected yet, drifting through interstellar space dark and silent, with their event horizons quietly defining the limits of where time still flows for the matter that surrounds them. The watch on your wrist is still moving. The second hand has not stopped. You are still here. And somewhere, 53 million light-years from this room, at the edge of a hole in space-time 40 billion kilometers across, a photon is just beginning the orbit that will sometime in the distant future bring its frozen, red-shifted image to a telescope as wide as the Earth. The image will be a still photograph of the boundary where time ends. It will not move. It will not change. It will sit there, perfectly still, against the orange ring of light that surrounds it, until the end of time itself. You will be long gone before it is taken, but the watch on your wrist is still moving. You are still here, and the second hand is still going around.